less than 10 seconds.
Hey everyone, Michael Unger here from the HR MacMillan Space Centre, once again joined by the incomparable, the scientist, the craft extraordinaire, that is Morgan Alford. How are you, Morgan?
Good. I can't complain with an introduction like that. How are you?
Well, I don't want to disappoint anyone out there, but we're only got a few more weeks that we have you because your contract's going to be up soon. But I've really enjoyed my time with you and the crafts that you've come up with each week. It's really helped us out, and hopefully helped out everyone out there that's been following along. And this week, it is summertime. So this week, we are talking about light. What is light, Morgan?
That is an excellent question. Light is a lot of things. Both a wave and a particle, sort of, I think.
Yeah.
We're going to be building a spectrometer this week. So we're looking at different sorts of colors through a lens. And honestly, just exploring how light in space occurs. And I actually have a question for you, as always.
Sure.
So why is space black?
Well, this is a really heavy question here, Morgan. How much time do we have? And I sort of take this approach to it. I can't tell you why it's black, but I can tell you that without the darkness, there would not be any light. So instead of asking why is space black, you may ask, well, why isn't it all white, or why isn't it all bright? The stars are there, and the only reason that we can see the stars is because of the spaces that are in between the stars, right? So what is that space, you may ask? And that's a really interesting question that starts to get us into what is the nature of space, and perhaps that absence of light may not necessarily mean that there's nothing there. It kind of depends on what we think of as things, as matter. And as we get into thinking about dark matter, this is a term that doesn't necessarily mean that dark matter is actually made up of matter. It just has mass. We don't know that it actually is like a substance. And it's not necessarily black. We call it dark, but we use that word dark to mean unknown. So to answer your question, what is it? Why is the space black? Well, that's all of the spaces that we're still trying to figure out, all of the mysteries of the universe. And, the universe is expanding and creating more unknowns. So that was kind of like a sideways answer. I think I kind of saddled through kind of your question. Didn't quite answer it, but hopefully intrigued some thought processes along the way.
Yeah, it's definitely interesting to think about, and very philosophical when you start to ask questions like, what is light, and what are colors, and what is darkness?
Yeah, certainly. And, on a very basic level, light is a thing that streams through my window. It wakes me up, and I don't necessarily like it when it's too early, because in the summertime, the sun is rising very early these days and setting later and later. So from my point of view, it's getting harder for me to stay up late to, say, look at the comet, because that gosh darn sun is taking so long to set, and also it's rising so much earlier, so I'm not getting enough sleep. So it sort of sounds like I have a love-hate relationship with light, but I do have one little thing that I do want to show you. So Morgan, do you know what this is?
It looks like a light bulb.
Looks like a light bulb. It's actually like a really cool invention that doesn't really have much of a scientific purpose, but actually created like a scientific mystery for many years. So this is called a radiometer. And inside you can sort of see that there's these little metally things. One side is silver and on the other side is black. And when it sits here on my desk at night, it doesn't move. And of course, if I jiggle around, it moves. But when sunlight hits it, it starts to spin. And the more sunlight that's hitting it, it spins even faster. And it's a fun little thing that I like to have. So there's a specific process that's happening as the sunlight hits the black side, and it's creating sort of like this vacuum inside there that starts the wheel to spin. And like I say, it has no scientific purpose because it's not giving me a reading at all. It's not telling me, oh, these are how many photons are hitting it at this exact time of day. But when I look at it and I see it spinning, I'm like, yep, there's sunlight. And when it's not spinning, nope, no sunlight. It's a really fun thing that I like to have on my desk that just tells me a really simple answer, but it looks really cool.
It does look really cool. And you know what? Sometimes you just need that confirmation. Is it sunny outside or not?
Yeah. Do I need to actually look outside and confirm that the sun is there? No, I'm going to look at my radiometer instead. And with that, Morgan, and for everyone out there watching, hopefully you have a lot of fun learning about spectroscopy. And please put into the comments or send us emails about any of your questions about this. And we'll see you again next week.
Enjoy. Hi everybody, we're back again for another week of doing spacecraft at home. This week we're looking at light, and so we're going to explore a little bit about why light is the way it is in space, why space is dark, where we see different colors on the planets, where that light source comes from, and so on and so forth. To better explain how our eyes see color, imagine a green apple. Why does the apple appear green? Light shines onto the apple, causing the apple to absorb every color in the light spectrum besides the color green. The color that the apple does not absorb is reflected back to our eyes, causing us to see green. Light is just a minor fraction of the entire electromagnetic spectrum. The electromagnetic spectrum contains all of the energy types that travel through space in a wave-like manner. Every day, light waves reflect off of objects and into our eyes, which allows us to see the objects. Within the small area of the electromagnetic spectrum that color consists of, there is all the colors that we can see every day, called the visible spectrum. The colors have different wavelengths that make them the colors that they appear. For example, red color waves are very long in length, while blue color waves are very short. Colors are also associated with temperature or the way that colors are perceived. Typically, warm objects look more red, like a heating stovetop or a red flame. Light plays a major role in how our eyes perceive color. The source of the light determines how our eyes interpret that color. For instance, if we're viewing a red shirt outside in the sunlight and then take it to look inside under a lamp, it may appear a darker shade due to the change in the color rendering index, or how the light makes colors appear. This has a large influence on the way that we perceive colors in space. So we're going to build an object today that allows us to view the different colors in the visible spectrum of the electromagnetic spectrum, which is called the spectroscope. The first thing we want to do, as always, is collect all of our materials at our workbench. So today, we are going to need a paper towel roll. If you are decorating your spectroscope, you're going to want to paint this with some acrylic paints the night before you actually build the spectroscope, so it's really got a long time to dry and get nice and firm again, so then you can really cut into it. If you are pressed for time, you can dry it for something like 2 to 4 hours, but that depends on your paints. So paper towel roll, paints are optional. You need a pair of scissors or some sort of box cutter. If you're using a box cutter or scissors and you're under the age of 13, please have a parent assist you with this craft today. You're going to need an old CD, a Sharpie, and some cardstock or recycled cardboard from some other product that you're not using any longer. So first thing we're going to do is take our paper towel roll, and we're going to make a small cut towards the end of the roll at a 45-degree angle. So if you were to imagine holding your paper towel on a table and making a straight line like this, that's about a 90-degree angle, you want to cut down about half of the angle. And you just want to make a small slit. Like that. And it's just got to be big enough that you can insert your CD into the slit and it can stay sturdy like that. Directly across from the slit, you're going to make a small hole. I'm going to do mine in the shape of a square just because it's a little bit easier. There we go. I broke into my cardboard tube a little bit there, but if that happens, you just have to reinforce the cardboard with some tape, which you are going to need to complete this craft anyhow. And then on the end of your tube that is furthest from your slit and your hole, you're going to trace the cardboard tube, and we're going to cut out this piece of the cardstock to seal to our tube with the tape that we just mentioned. So here I'm using my Sharpie to trace it, just roughly. It doesn't need to be perfect. And then cut out the shape that you just traced on the cardboard. And seal it to the end of the tube from which you traced it. So we've got our tube fully sealed. We've taped our cardboard stock to the top of the tube, and I've also reinforced down here with some tape where I accidentally cut into the cardboard outside of the square for viewing. Now all we want to do is take our CD, insert it into the slit like we demonstrated previously, and then using the square across from the slit, we are going to view the light being reflected off of our CD and into our eyes. And so this is gonna change depending on your light source. You can just view through where you are doing the craft, and then I'm going to recommend you take it outside and see if the sunlight affects the spectrum of light that you are able to view, as well as under a lamp. And in your lab notebook, make some recordings of your observations and compare them and let us know what you see. I'll let you go play, and we'll see you guys next week for some more crafts.